We're all familiar with the idea of dividing one number by another and getting a remainder. But have you ever thought about how deep this idea really is? It turns out, this question has a core place in modern cryptography. In this video, I'll introduce modular arithmetic, and hopefully you will leave with an understanding of just why/how some of it works, as well as how it's used in modern crypto systems. We'll also take a side tour to continued fractions. Think of this as a guided exploration in which you, the viewer, are the explorer, while I help you along, with emphasis on playing around with numerical examples. Let's dive in. In school, we're taught that we can divide one integer by another and get a result called the quotient, plus some remainder. Sometimes we only care about the remainder, so we could say 46 has remainder 1 on division by 5. Us mathematicians have invented some notation for this, called mod. Instead of saying 46 has remainder 1 on division by 5, we say 46 is congruent to 1 mod 5. That triple line equals is the symbol for congruent to, and mod stands for modulo. You can think of the congruent to symbol as kind of being almost the same as an equal symbol, but not quite. We'll show that we can do many of the same things, like add something to both sides, subtract, multiply, etc. Division is a bit weird though, which I'll get to in the modular inverse section. We can think of all this in a bit of a different way. The reason 46 over 5 has a remainder of 1 is because we can keep subtracting 5 from 46 until we get to 1. But we don't have to stop at 1. What if we stopped at 6? Or minus 4? We'd have 46 is congruent to 1, is congruent to 6, is congruent to minus 4 mod 5? Remember, we're making the rules here. Should we let this be true? Why should it be, based on our original definition? Well, to clear things up, here's a more formal definition. When we say A is congruent to B mod n, we mean the same thing as A minus B is divisible by n. So 46 is congruent to 6 mod 5 because 46 minus 6 is divisible by 5. Can you see why we can add and subtract any multiple of 5 now? From this definition, it's not immediately clear why the congruent symbol is quote-unquote almost an equal symbol, and it's good to think about why. Why can we add or multiply by the same thing to both sides? Here's a hint. If A minus B is divisible by n, then so is c times A minus B for any integer c. Then see what happens when we expand. To get a feeling for this world of mod, let's try and compute 20 times 5 mod 7. Well, that's 100 mod 7, and 100 over 7 has remainder 2, so 20 times 5 is congruent to 2 mod 7. But the calculation got pretty big there. We had to calculate 100 over 7, and that's effort that we don't like. What if we said 20 is congruent to minus 1, so 20 times 5 is congruent to minus 1 times 5 is congruent to 5 is congruent to 2. Would that be valid? Try creating some more examples, try both ways of computing, and see if the results are the same. Do you believe it? If you want to honest to goodness prove this way of calculating, by the way, here's a hint. Minus 1 can be written as 20 plus a multiple of 7. A natural extension of our thoughts might be, since we can save effort during multiplication, can we save effort during exponentiation? This is where the amount of effort saved really starts to show. Let's try finding 3 to the 20 mod 7. Just like in the multiplication example, we could compute 3 to the 20 and then find the remainder. But that's clearly way too much effort to do by hand. 3 to the 20 is a huge number. What could we do instead? It turns out that this question of how we can save effort in the weird and wonderful world of mod is at the center of modern cryptography, which is all around us these days. To reduce our workload, we could make use of exponent rules from school. 3 to the 20 is 3 squared to the 10, and 3 squared is 9, which is 2 mod 7, so 3 to the 20 is congruent to 2 to the 10. Hold up, is this valid? Well, from our experiment in the multiplication section, we might feel comfortable replacing the 9s with 2s one at a time like so. So 9 to the 10 is congruent to 2 to the 10 mod 7, and in fact we can generalize. Replacing numbers with letters, we get a to the b is congruent to a mod n to the b mod n. From here, you might notice that 2 cubed is 8, which is congruent to 1 mod 7, which we can use to our advantage like so. So overall, 3 to the 20 is congruent to 2 to the 10 is congruent to 2. The effort-saving idea we use here is to write 10 as a multiple of 3 plus some remainder, so we can use the fact that 2 to the 3 is congruent to 1 to cancel things. Let's do another example. Say, what is 5 to the 58 mod 26? Pause the video and try yourself if you want. After searching for something that might make life easy, we might notice that 5 to the 4 is congruent to 1 mod 26, since 5 squared is congruent to minus 1, and we can square both sides. So, using the same trick as before, we can write 58 as a multiple of 4 plus some remainder. In other words, 4 times some integer q plus the remainder, which is 58 mod 4. Note that here we aren't caring about the specific value of q. Then, similar to the previous example, we can use some exponent rules. In the end, we get 5 to the 58 is congruent to 5 to the 58 mod 4 mod 26. So to recap our examples, we have, since 2 to the 3 is congruent to 1 mod 7, 2 to the 10 is congruent to 2 to the 10 mod 3 mod 7, and since 5 to the 4 is congruent to 1 mod 26, 5 to the 58 is congruent to 5 to the 58 mod 4 mod 26. Can you see the general case? If we know that a to the b is congruent to 1 mod n, then a to the c is congruent to a to the c mod b mod n for integers c. These are some pretty neat tricks, right? They definitely let us save a lot of time. In fact, what's on the screen is part of the maths backbone of a modern encryption system called RSA, which I'll cover in more detail later. Is a half an integer mod 5? This question seems a bit nonsensical at first. You might ask, if a half isn't even an integer, how can it be 1 mod 5? Well, 2 times a half equals 1, so what we're looking for is the number x such that 2x is congruent to 1 mod 5. Is there such a number x? We could try every option mod 5, namely 0 up to 4. Indeed, you might find that x equals 3 works. In other words, a half is congruent to 3 mod 5. Crazy, right? Since 2 times 3 is congruent to 1 mod 5, we call 3 the modular multiplicative inverse of 2 mod 5, or modular inverse for short, just like how we would call 0.5 the multiplicative inverse of 2 in the real numbers. So more generally, if u times v is congruent to 1 mod n, then u and v are modular inverses of each other. I encourage you to pause and try this idea with some more examples. What is 1 over 2 mod 9? How about 1 over 3 mod 10? A question worth asking is, does the modular inverse always exist? Let's try and find 1 over 6 mod 8. Using the same technique as before, we're looking for the number x such that 6x is congruent to 1 mod 8. That means 6x minus 1 is divisible by 8, so 6x minus 1 must be even. Can you see the problem here? 6x minus 1 is odd since 6x is even, so there's no possible x. In other words, 6 does not have a multiplicative inverse mod 8. We can actually extend this idea to show that k to the minus 1 does not exist mod n if k and n have a common factor greater than 1. By the way, I'm saying k to the minus 1 instead of 1 over k here, just because of convention. Can you do it? Here's a hint, we can use the same technique as before. I'll introduce some more jargon here. We'll say two numbers are coprime if their greatest common divisor is 1. So for example, 8 and 11 are coprime, but 12 and 15 are not coprime because they're both divisible by 3. So with this coprime word, we can rephrase our statement slightly. We're trying to solve for x in the equation kx is congruent to 1 mod n. we get kx minus 1 is divisible by n by definition, so we'll write L times n here to mean some integer multiple of n. Now let's rearrange to get kx minus ln equals 1. We'll let d be a common factor of n and k. Then kx minus ln is divisible by d, since kx and ln both are. But that means 1 is divisible by d, which is only possible if d equals 1, so k and n must be coprime in order for the modular inverse to exist, and we're done. This is great and all, but when exactly does k have a modular inverse mod n? We've shown if k and n aren't coprime, then the modular inverse doesn't exist, but what about if they are coprime? Try a few examples where k and n are coprime. Do you believe that there's always a modular inverse if k and n are coprime? In the real world, by the way, modular inverses are the key step in many cryptosystems to enable us to decrypt messages. Now, let's think about a seemingly unrelated tangent to all this, continued fractions. To get a grasp on this, we'll play around with 29 over 11. 29 over 11 is 2 plus 7 over 11. But 7 over 11 is 1 over 11 over 7. We can replace 11 over 7 with 1 plus 4 over 7. And we'll continue growing the fraction like this. This is what we call a continued fraction, where the numerators are all 1. For convenience, by the way, we often use these numbers here to describe the continued fraction without having to write all the fraction lines. We'll wrap these numbers in square brackets and call them the quotients of the continued fraction. So the quotients of the continued fraction for 29 over 11 are 2, 1, 1, 1, and 3. Now, you, being the ever content-hungry viewer, might ask, why should we care? Well, it turns out that continued fractions give us a way to quickly compute modular inverses. Stay with me and we'll discover the magical way continued fractions relate to modular arithmetic. We can approximate the continued fraction by cutting it off at some point. For example, if we cut it off here, we get 2. So we'll say 2, or 2 over 1, is the first convergent of 29 over 11. If we cut it off here, we get 2 plus 1 over 1, which is 3. So the second convergent is 3 over 1. If we continue like this, we get the convergence 2 over 1, 3 over 1, 5 over 2, 8 over 3, and 29 over 11. As a side note, by the way, you might notice it can get kind of annoying having to compute convergence like this. There couldn't possibly be another way, could there? I'm totally not foreshadowing. Let's plot the convergence side by side in a table, like this. Also, we'll add in the quotients on top, and these zeros and ones to the side. There's a reason for laying everything out like this. Do you see a pattern? How about now? How about now? The pattern is that we can generate the next convergent just by looking at the previous two. To fill in the number x at this position, for example, we take the quotient in the same column as x, multiply it by the number to the left of x, and add the number 2 spots to the left of x. So here, we would get 2 times 1 plus 0, which is 2. And we can do this again for the next number along. 1 times 2 plus 1 is 3. Then we can continue like this and fill in the whole table. This is amazing! It feels like we're computing the continued fraction from outside in. When we were calculating the convergence earlier, we had to expand each one from inside outwards, and they seem to have absolutely no relation to the previous conversion. but we've discovered that they are related. So this magic box gives us a way to reduce our workload hugely, since we can compute each conversion from the previous ones, rather than having to start from scratch each time. I can't stress enough how magical this is. But there's something even cooler, and it's hiding inside some 2x2 squares. What do you notice about the products of the diagonals? They're one apart, right? How about if we look at the next square along? Again, the products differ by 1. If we move along, looking at the squares and calculating the differences of the diagonals, we get our observation is that the differences seem to alternate between -1 and 1. So what, you might ask? Well, if this is true, then notice, if we look at the last square, it gives us a solution to the equation 11x plus 29y equals 1, namely x equals 8 and y equals -3. Now, if we take both sides mod 11, we have a solution to the equation 29x is congruent to 1 mod 11. But hold on a second, that means we've computed the modular inverse of 29 mod 11. Now that is awesome, because now we can use the magic box to quickly compute modular inverses. Who would have thought that modular inverses were related to continued fractions? This is just one of the many ways two seemingly distant areas of maths connect beautifully. And if we ever get to the point where we understand this connection to our bones, well, that's the feeling all mathematicians dream of. It's also worth mentioning, there's a nicer way to find quotients of a continued fraction than writing the whole fraction out. Here's a sneak peek of how to find the quotients more effectively. Can you see why this method gives us the quotients? This is certainly worth thinking about, and it's known in the business as the Euclidean algorithm. If you feel up to it, you should try and prove the amazing things we've noticed about the magic box, although I would say that proof by induction helps a lot here. Remember, there are no coincidences in maths. The things we've discussed so far are actually some of the key mathematical building blocks of an encryption system called RSA. RSA is one of the first modern crypto systems, and variants are still often used today. Say we want to set up a number sharing system between us, so that you can encrypt a number and send it to me, I can decrypt it, and no outsider can find out the original secret number, even if they know all the information that we've exchanged between us. Sounds pretty hard to come up with a system that works, right? Well, RSA solves this problem in a rather beautiful way. Here's how it works. First, I choose two very large prime numbers p and q, which I keep to myself. Then, I compute their product n and send you n. In other words, n is public knowledge, since an outsider could intercept my message to you that contains n. But the clever part is, even if an outsider knew n, they wouldn't be able to obtain p and q, because it turns out factorizing large numbers like n is very hard, since we can't do much more than simply guess factors. And by very hard, I mean it would take a computer on the scale of quadrillions of years to factorize n if we chose p and q to be large enough. So yeah, factorizing n ain't gonna happen. Next, I compute a value, which we'll call phi, as p minus 1 times q minus 1, so that weird Greek symbol there is phi. This is easy for me to do, since I know both p and q, and multiplication is relatively easy for computers, even for huge numbers. Once again, no one else could know phi, since they would have to know p and q. I keep phi to myself. Now I choose a number e which is coprime to phi. In the real world, we usually use the prime e equals 65537. Again, I send you e. So to recap, All an outsider could know is n and d. Only I know p, q, and phi. Using the magic box that we saw in the continued fractions section, I can compute the modular inverse of e mod phi. Call this d. So e times d is congruent to 1 mod phi. This is also why we chose e to be coprime to phi, so that the modular inverse actually exists. Again, only I know d, since no one else knows phi. Knowing phi and d is the core part of the magic of RSA. We'll see how everything comes together soon. Next, to encrypt your secret number, m, which you want to send to me, you compute the encrypted number as m to the e mod n. You can do this since you know m, e, and n. Does this meet our requirements of no outsider being able to decrypt it? Yes. As far as we know today, from the public information, there's no way of getting m back from m to the e mod n without just trying every possibility mod n, which again would take so long that we can just ignore the possibility of that happening. But then how can I decrypt it? Well, that's why RSA is so astounding. To decrypt, I make use of the private information only I know. Do you remember the two time-saving tricks we derived earlier? Let's write them out again. Now, there's a theorem called Euler's theorem that says m to the phi is congruent to 1 mod n, which unfortunately we didn't have time to cover in this video. That damn Euler has so many theorems named after him that if you go off to research Euler's theorem on your own, there's a good chance that you'll end up reading about the wrong stuff. So be careful, I guess. There's also a small caveat that m has to be coprime to n for Euler's theorem to work. But p and q are so large that the chance that m and n aren't coprime is essentially 0. Does m to the phi congruent to 1 ring any bells? We have something to the power of something is congruent to 1 mod n. That looks suspiciously like our little time-saving trick. We can apply that trick in our case to get n to the c is congruent to n to the c mod phi mod n for any integer c. Following this logic, what if I take the encrypted message m to the e mod n and raise it to the power of d mod n? Again, this is possible because computers are good at exponentiation. By the first trick, m to the e mod n to the d is congruent to m to the e to the d mod n. Now we can manipulate a bit. This is where the magic happens. Remember, we've specifically chosen d such that e times d is congruent to 1 mod phi, so everything cancels. I've got back m mod n. Now, let's assume we've agreed beforehand that the secret number is lower than n. Then m mod n is exactly m, so I've got the original secret number. Phew, that was a lot of letters. Let's get on to a real example and see how RSA works in practice. We'll use small numbers as a starter, say p equals 11 and q equals 23. N is p times q, which is 253 in this case. Since the numbers in this example are small, factorizing 253 is relatively easy, but that won't be the case with larger p and q. Phi is p minus 1 times q minus 1, which is 220. We'll choose e now, say e equals 3. Remember, e has to be coprime to phi in order for e to have a modular inverse mod phi, and indeed 3 is coprime to 220. Finally, we compute d as the modular inverse of e mod phi, which is 3 to the minus 1 mod 220. For brevity, I'll skip over using the magic box to compute this, but feel free to go into the details of that if you want. In the end, we get d is 147. Let's go through encryption. If you want to send me a secret number, say, I don't know, 69, you would send me m to the e mod n which in this case is 69 to the 3 mod 253, which is 115. To reiterate, the only things an outsider could know are n, e, and the encrypted number. But there's no way of getting the secret number out from just this information. However, all I need to do to decrypt is compute the encrypted number raised to the power of d mod n, which in this case is 115 to the 147 mod 253. Again, it's easy for computers to do exponentiation in the world of mod, since because of our time-saving tricks from earlier, all they need to do is repeatedly multiply by 115 and then take it mod 253 at each step, so the calculation never gets bigger than 253. So if we use some Python code to evaluate 115 to the 147 mod 253, we indeed get that 115 to the 147 is congruent to 69 mod 253, which is the secret number. Neat. Our current baby version of RSA only lets us exchange numbers, specifically numbers smaller than n and coprime to n. Since n is so large, having to be smaller than and coprime to n shouldn't be an issue, because the chance of a random m being coprime is practically 100%. So all we need is a way to turn text into numbers, and ta-da! We've got a way of sharing encrypted messages. The convention in practice is to use ASCII character codes, and I'll skip the details, but if you're interested, there's a link in the description to some more info. So to play around, can you decrypt this secret number? Something like Python code might help a lot here. If you get it, feel free to say what the secret number is down in the comments. One last thing, I've hidden a secret message in this video. My parting challenge for you is to go on a bit of a cyber hunt and find out what I've hidden. You'll need to be equipped with the knowledge of what we've covered in this video. Good luck! I hope you enjoyed this dive into modular arithmetic basics and RSA. What we've covered amounts to just a small dot in the vast world of modular arithmetic to be explored, but I hope this video gave you a feeling for how at least some of it works. If you want to go further, I'd recommend playing around with continued fraction expansions for irrational numbers, and looking at some of the ways RSA might not be as secure as it seems. Thanks for watching! This is my first attempt at anything like making a YouTube video, so constructive feedback would be greatly appreciated. Thanks to the Manim community for making my animation work 10 times easier, and of course, I'd like to thank 3B1 Brown for giving me the motivation to create this video, because it's definitely not something I would have decided to try out if not for his Summer of Math exposition.